everybody. So, class recording has started. So today, for the first part of class, we want to spend some time discussing a little bit more about the states of matter. I know that you guys are familiar with states of matter, but what we want to talk a little bit more about, instead of just identifying states of matter, is talk about, why do they happen? And we use the kinetic theory of matter to explain states of matter. So, by virtue of the fact that it's called the kinetic theory of matter, you should be able to tell me a couple of things, all right? What's one thing you could maybe tell me about the kinetic theory of matter based on its name? It deals with motion. That's what part of the name? That's the kinetic part, okay? So, the fact that it's kinetic theory of matter, it deals with motion. The fact that, okay, Devin, go ahead. It deals with matter because it's the kinetic theory of matter. What does it have to do, or what does it have to show us about matter? Well, what's the only word in there that we haven't, theory. What do theories do? They explain, right? So what we're doing here is explaining states of matter through motion. Okay? And that's what we're going to focus on here for the first part of class today. So, the kinetic theory of matter. A theory that all matter is made up of tiny particles. Now, when we say particles, right, we talked about that could be atoms, if you're talking strictly about an element, or it could be molecules, if you're talking about a compound, right? A theory that matter is made up of tiny particles, which are atoms or molecules, that are in constant motion. That's the kinetic part. And I think I gave it to you on Friday. So, yeah. That's why on the board it said from Friday. So.
There's an extra one right here, too.
You guys grabbed it. I knew it. I'm trying not to know. Yes.
See in here, there's an extra one.
So, I think most of you are familiar with the idea that as the temperature of a substance increases, the particles move faster. Yes, sir.
The outline says as temperatures increases, length increases in particles.
How about, yeah, that is, yes. Modify it so it says this.
Okay.
As temperature increases, particles move faster.
Okay.
Or there's more motion or something along those lines. And then, what we realize, or what we figure out too, is that if you have two substances that are at the same temperature, their motion is not always the same. And that heavier particles move more slowly than lighter particles. So when we have matter, all the particles move. As the temperature increases, those particles move faster. Yes, Lauren? But there is one more factor that we have to consider when we're explaining the states of matter. And that factor is the forces of attraction. So, there are two factors that we consider when we are trying to explain matter. One is the motion, two is the forces of attraction. Keep those things in mind as we keep going, all right? Because we're going to come back to those again and again and again, right? So, the motion of the individual particles, more specifically their energy, right? And the forces of attraction determine the state of matter that something exists in. Give that a second. So 2 factors, right? Energy, forces of attraction. All right, good there? Good? Okay. So, let's start talking about the states of matter that we know exist. I think most of you are probably familiar with the big 3, right? Okay. So, solid, liquid, gas. Yes? I think most of you have probably heard of those before, I'd imagine. We did talk about this on a little bit on the previous outline, but we want to talk a little bit more about it here. Okay. All right. And I think that most of you know that if we want to go from solid to liquid or liquid to gas, what do we have to do? Heat it, right? Or do what to the energy, Jules? Increase the energy, right? So as we go down this list, solid, liquid, gas, energy increases. And we'll talk about that a little bit more as we go along. But there are other states of matter that exist out there that just don't happen very often here on Earth. But they do exist, right? So, the first one is this lightning bolt. Not the Eiffel Tower, but the lightning bolt that's hitting the Eiffel Tower, right? And we refer to that state of matter as plasma. Okay? So, if... What? Yeah, very much so. Anything tall and pointy lightning hits all the time. No, because a lot of times they'll have it set up where they actually have a lightning rod on top of the Eiffel Tower, because if you improve the chances that you know something's going to hit it, you have just like a big wire that runs into the ground, so all that electricity just goes straight into the ground instead of shocking other people. So you actually kind of want the lightning to hit tall things instead of hitting other things where people are. So. Okay. Also, too, I mean, lightning hits airplanes a lot too, but because the airplane is an enclosed metal container, the electricity spreads around the outside of that container and doesn't hit the people inside. Just like when say again? In an airplane? Yeah. So. Yeah, it's probably. I mean, it might be scary, but nothing happens really, right? It's really loud. Yeah, it's really loud, but yeah, it's so. Sounds like it's gonna fall. All right, so plasma is on the far upper end of the spectrum. When particles gain very, very high energy. When we talk about particles, I said that we could talk about 2 things. We could talk about atoms or we could talk about molecules. Okay? But what happens as we increase the energy of those particles more and more and more, atoms don't stick together anymore. We know from earlier chapters that atoms are made out of what? Electrons, protons, neutrons. If you give them high enough energy, they don't hold together as atoms anymore. The nucleus just falls apart and becomes a bunch of separate protons and neutrons. And electrons aren't really attracted to the protons because they just have so much energy anymore, right? So plasma is separate positive and negative charges. Just a bunch of pieces parts, not even atoms anymore. But it only happens at extremely high temperatures or other forms of extreme energy, okay? And while here on Earth it doesn't exist very often, in the universe, an overwhelming majority of the mass that is out there in the universe actually is in the form of plasma. Stars, like our sun, are technically not atoms, or a lot of it isn't really like elements, just a bunch of pieces parts. And they put the pieces parts together into atoms, right? That's what we call nuclear fusion. Here on Earth, that doesn't happen very often, but in the big picture of the universe, it happens quite frequently, where the matter that's out there really is just a bunch of pieces parts that needs to be put together. Okay? Good there? All right. So plasma is on the very, very high energy end of the spectrum. What do you think? Where do you think we're going to next? The very, very low energy part of the spectrum. And on the very, very low end of the spectrum, we talked about the Bose-Einstein constant. We did this, right? Okay. Oh, the other class I didn't do it in detail. Okay. Good. So Bose-Einstein constant. I thought it was you guys. Okay. I didn't. I'm sorry. I knew there was one. I assumed because you guys were behind that you hadn't done it before. My bad. You know what? I know. I gotta stop chit-chatting about plasma.
Yeah.
You know what happens when you assume, right?
I know what happened. I don't know now.
All right, you got this? Just copy it down. Did you write it down?
No,
Sometimes it's easier to see.
she doesn't. It's Monday.
I'm just saying sometimes it's easier to see. When you assume.
You have to write down the list. Oh, no, I got it.
All right, we got this.
It's the very, very low energy.
Very, very low energy. It's like I think the second line. All right. While Bose-Einstein condensate and plasma do exist, and in the case of plasma, they exist a lot out there in the universe, we're going to stick with the states of matter that we deal with most often here on Earth. So, let's start with gases. Now, here's a picture of gas. You guys don't have this picture, but I think you're probably familiar with it and what it represents. So, what can you tell me about the particles that make up a gas? What's one thing? Very spread out. What else? They move really, really fast. Is that what okay. All right. So very spread out, move very, very fast, and that's true. And so if we look back at kinetic theory, it explains why a gas does what a gas does. So particles of a gas are in constant random motion at very, very high speeds, and that means, right, when it says on that second bullet where it says gases have more energy than liquids or solids, if you make sure that we understand that that's particles of a gas have more energy than particles of a liquid or particles of a solid. But that's only absolutely true if we're talking about the same material. Not all gases, not all particles of all gases have more energy than all particles of liquids and all particles of solids, only if we're talking about the same material as a solid, liquid, and a gas. So very high energy, okay? But also spread out. And that means that the motion of one particle is not affected by the other particles. We said that kinetic theory tells us there are two factors that explain why matter behaves the way it does. What are the two factors? You flip it over to the front side. What two factors determine why matter behaves the way it does, or is in what state of matter? Two factors. Temperature is kind of a sort of more specific term of energy. Okay, so energy and front side. Yes. Letter D. Attraction. Forces, right? Energy and attraction. Those are the two factors that we have to consider. So, when we talk about a gas, right? How much energy do the particles have? A lot. How much attraction do they have? Not a lot. Because why?
They're spread out.
They're so spread out, right? So in essence, the individual particles don't attract each other at all. And so we know when you started learning about states of matter back in the 2nd grade or the 4th grade or whenever you started learning about it, there are 2 characteristics of gases, right? What do gases do? Take the shape of their container and the volume of their container. They completely fill it up, right? Because the particles move real fast and they don't hold on to each other. So that allows the gas to completely fill the container that they're in. They take up the shape of that container and the size of that container. Which is something that we know, back, like I said, when we started first learning about states of matter, but when you talk about it now, energy and attraction, lots of energy, little attraction, we'll just completely fill up the space. Okay? So, one of the ways that we can use to explain this, or kind of hopefully make a little more sense out of it, is come up with an analogy, something we're familiar with, right? So if we talk about kids at school, there are examples of things at school that represent our different states of matter. So if we think about elementary school more so than like you guys, right? What during an elementary school day would be representative of a gas? Recess, right? What do kids on recess do? Run around, right? How far do they go? As far as the playground will take them, right? Okay? If there's already a class on recess, and we let another class on recess, does that affect what the first class is doing? Could, depending on the size of the playground. But if the playground's big enough, can we let another class out under recess and, we just go, right? While some kids play with each other on recess, right, they play kickball or whatever, foursquare, or whatever it might be, right? Sorry. While some kids engage in the same activities as other kids, right? So, you don't have to. You can pretty much do whatever you want on recess. Just like the particles don't have of a gas don't have any attraction for each other. Good there? Mixing occurs real easily, right? Somebody sprays body spray in the hallway. What happens?
Takes up the whole hall.
Takes up the whole hallway. But there's already something in the hallway, right? The hallway is already filled with air, but if we add another gas, those 2 gases just mix very readily because there's so much space in between the particles that we can get more than one gas in the same space. Okay? Good there. All right, let's go next. Back in 2nd grade or wherever, you learned that liquids have 2 characteristics. What are the 2 characteristics of a liquid? Var. They take the shape of the container they're in, but they keep their volume, right? Just because we take the shape of something doesn't mean we completely fill it up, right? You can take the shape of the bottom of something, but not completely fill the whole space, right? And that's what liquids, right? They have a definite volume, but no definite shape. Okay? Oh, you give me that one. Not like the way
It's not like that important.
Okay. Do you not like the way I say volume?
Yeah. I was just. You say it. Wait, how do you say it? You say it.
Volume.
Volume.
Volume. That's you.
It just seems like more work. Volume. Volume.
How do you say it?
I say volume.
Volume. There's an E.
Just
I do say valence instead of balance. So. I actually got much better this year because last year, my students last year made fun of me all the time because I would say electricity. I make a very, like when I'm talking fast I do, but I think about it now and I try to say electricity. Yeah. Electricity. Like with a Z instead of a C, instead of an S. But now, like, because my students last year gave me a hard time about it all the time. And so now, like this year, I made a very conscious effort to be like, electricity. Like, so. I suppose this is good in a way that you guys actually have to listen to me to like figure these things out. All right. Particles of a liquid move more slowly than gases, and they are more closely packed together. So, move more slowly means what about their energy? Less energy. If they're closer together, what else does that mean? More attraction. Okay? Liquids, particles of a liquid, have less energy than gases, but more energy than solids. Keeping in mind that means we're still talking about the same substance. That's just something you kind of have to, there's no place for it, but you should understand that idea. The attractive forces between the particles, strong enough to affect the motion of other particles to a certain degree. So because we're more closely packed, the attractive forces start becoming more significant. The particles can still move, but not as quickly as gases. They don't have the freedom that the particles of a gas have. That being said, if we go back to our analogy, kids at school, what part of a school day might be representative of a liquid? Cafeteria is a pretty good example. Do you have the ability to move about the cafeteria?
Not really. Mrs. Murphy would kill us if we moved. Oh yeah, Mrs. Murphy. She'd be like, I hated her.
Let's talk about now.
She sent me to the principal's office because I didn't throw a cheese stick. Someone else did, and I got in trouble for it.
Not that you're bitter and holding on to your anger for a long time or anything like that.
No, I let it go.
Yeah, I can tell. You guys are gonna be at your 20-year high school reunion. You're gonna be like, remember?
She's gonna be dead. She's like 95.
You're gonna be still telling the story.
Yeah, she's gonna be dead now.
Right now, like 3 years ago.
Yeah.
In the cafeteria, individual particles. You have the ability to move around, but you have to move around other people. People carrying lunch trays, the tables in the cafeteria. If you're going to the line to buy something to eat, right, you got to go around the pillars and get in line. You have the ability to move, but not as quickly, not as freely as you would out on recess. Or if we talk about here at school, when you walk through the halls in between periods, you have the ability to move. You can move in different places, but there are things you have to dodge, right? You have to dodge other people. You have to dodge humongous backpacks, whatever it is in the way, get under the stairs, whatever you need to go. I need to turn left, but everybody's going straight, right? These are all things that affect your motion. You still have the ability to move, but you can't move as quickly or as freely as you did before. Okay? Good there? All right. That leads to our behavior of our liquids, right? No definite shape, but a definite volume, right? Forces of attraction are strong enough to hold the particles are not strong enough to hold the particles in one place. They're free to move past each other, but they can take the shape of the container. Yes, Jafar?
So those lines just there.
Where? C and D?
Oh, we have to.
You don't have to write anything, but that's what goes in those spaces. And those two characteristics of the liquid can be explained through kinetic theory. Less motion, more attraction, less freedom. You can move around a little bit, but you're still sort of confined. All right, good there? Finally, solid. What two characteristics of a solid did you learn back in 4th grade?
Definite shape doesn't matter.
Definite shape, definite volume. Sorry, definite shape, definite volume. Yeah, I get it. Volume. It's like I'm speaking French now. That's like French. The volume. Sounds like a French accent.
Oh my god.
As we go through the progression, particles that make up a solid, what's happening to their energy compared to liquid? Less energy, right? But if there's less energy, what takes over more? Attraction. Less energy, more attraction. And when we say solids have the least amount of energy of all states of matter, that's not entirely true, just for the states of matter that we encounter here on Earth most often. No, we said plasma is very, very high energy. Bose-Einstein condensate. Yeah.
And then, so,
Bose-Einstein condensate has the least amount of energy. The particles have the least amount of energy. Because, Devin, we said that, if you look up back on the front side, Bose-Einstein condensate only occurs at temperatures near absolute zero. And absolute zero is the absence of motion, where the particles would completely stop.
What would happen at absolute zero?
Well, in reality, we can't get to absolute zero.
But like, if you don't know what would happen.
Well, what happens is, we kind of talked about this the other day with Bose-Einstein condensate, right? That, but if you don't have any matter, there's no temperature. Does that make sense? Okay. So, hold on. Minus 450-ish, something like that. So, somewhere around there. So, Pat, what would happen when we get to absolute zero? Well, the answer is we'll never know, because we can't actually get to absolute zero. Because the way that we make things colder is we put something colder next to it, and it loses energy to that colder object. Does that make sense? But you can't get to absolute zero because there's nothing below zero for you to lose energy to. Does that make sense? But when we talk about like Bose-Einstein condensate, in a solid, so if we take our analogy, right? You guys right now are representative of a solid. You're in a fixed position. Everybody has their own place, orderly, but you're not still, right? You're writing, you're moving a little bit, you're fidgeting, whatever it might be. At Bose-Einstein condensate, that individual motion stops. That all of you would have to do exactly the same thing at the same time. Does that make sense? So that, like to go to the bathroom example, right? So things start becoming heavier, harder to move, because they don't have the individuality of the particles that they have even at a solid state. Does that sort of make sense? Lauren, good.
Maddie has a question, and it would be, if this room was like normal,
Yeah.
and then that room was like plasma,
Okay.
and then we walked in it, absolute zero. Like, would it be too cold to like feel cold?
You like shout out like a solid yes.
Maddie, we'll learn. Lauren, tell Maddie that if she wants to know the answer to this question, we'll learn a little bit later on that energy flows spontaneously from high energy to low energy. That's to balance everything out. So if we go into a colder environment, energy flows out of us and into that colder environment to warm up that other environment, but in the process we get colder. Does that make sense?
The environment gets warmer, so technically the environment is killing.
Well, it could.
Yeah.
If there was such a big difference in energy that it took all the energy out of us, right? Which is what happens when you get like hypothermia.
That makes sense now.
So energy flows from hot to cold.
Can you die from that?
Oh yeah, because your body works on chemical reactions, And we learned in the last chapter that chemical reactions go faster when you're warmer and slower when you're colder. So as you get colder and colder, those chemical reactions that make your body move and work, like your heart beating and your brain working and stuff like that, they slow down to the point where they don't work anymore. And if chemical reactions don't work, your body doesn't function. All right, good? As motion decreases, attraction increases. So in a solid, the particles are strongly attracted to one another, and that keeps them in place. Here, as you sit in this classroom, the chairs and the desks sort of artificially keep you in place, but they keep you in this nice orderly fashion. That's what a solid is. All these individual particles kept in nice orderly fashion because of the forces of attraction. As a result, definite shape, definite volume, you guys don't fill this room. Even though there's more space for you to spread out, we maintain this shape. Does that make sense? Good with these. Okay. The next outline deals with changes of states. The outline that you guys picked up on the back today. There was one back. It's got the triangle on it, okay, which is the triangle you've seen before, but it's a different sheet. Yeah, it was on one of your previous outlines. When we talked about physical changes. So, if we want to talk about, if we need to change what state of matter we're in, there are two factors that we need to address. Well, temperature is the energy, and then we also have to address the energy and attraction. So how hard or easy it is to turn something from one to the other depends on the energy, depends on the attraction. When we go from one state of matter to another, a change of state, okay, we refer to that as a phase change or a state change, where a substance changes the state of matter. Phase changes or state changes are reversible physical changes. If we refer to something as a physical change, what does that mean? What color? If it's a physical change, what does that mean? Well, bending it is a...
It stays the same substance.
Properties stay the same, or properties change, but it's still the same substance. If we use our analogy in school, right? Right now you guys represent a solid. When the bell rings, you'll turn into a liquid. But when school lets out, you turn into a gas, and that's that's how it works, right? But it's still the same you, right? The identity of the substance hasn't changed, just the energy has changed. So good.
On one of our outlines, it says, like, for one of the indications of a chemical change, it says that a gas is formed. So, does that mean that it's going to become a gas as a chemical change?
No. Remember we said that those indicators... No, that's a fair question.
No, it's just like, because on the quiz, then I know I got it wrong.
One of those, we said those indicators of chemical change, color change, precipitate, gas, and energy release, just because one of those happens doesn't necessarily mean we've made something new. Right? A chemical reaction means we actually have to make something new. So, composition of substance change, but there are significant changes in energy. But we know that when a substance changes its energy, that's not the only thing that can happen because of conservation. If one substance gains energy, what else has to happen? Something else has to lose energy, and vice versa, because of the whole conservation idea. So, during a phase change, Energy is transferred between the substance and the surroundings. Sometimes energy flows into the substance. And when that happens, we call it an endothermic phase change, right? That's letter B. But sometimes our substance will lose energy to the surroundings. And when that happens, that's exothermic, and that's letter C on your outline. So if you look, B and C are endothermic and exothermic, right? B is endothermic. We have energy flowing into our substance from the surroundings. But C, exothermic, energy is released from the subject, or from the substance into the surroundings. Okay? So, just to, Maddie, like to kind of build off the question from before, okay? When you go into a cold room, energy flows out of you and into the room. That's an exothermic change. But what does it feel like to you? You're getting colder. So like, make sure we keep that straight, right? You're getting colder, but that's because you're losing energy. Generally, we think of exothermic things as hot. Yeah, that's true, but the stuff around them gets hot. Does that make sense? Like, endothermic energy flows into us. We would feel warmer, but everybody else in the room would feel colder. Does that make sense? Right, so when we get exothermic confused sometimes because exothermic we think of like hot things. Technically here, if you're losing energy, you would actually get colder. Does that make sense? Until they become the same temperature. Because energy flows from hot to cold until they become the same temperature, because then there is no hot or cold, they're the same. Does that make sense?
Yeah.
Okay. And we'll do more of that next week when we talk about energy moving around and stuff like that. Alright, so let's take a phase change that I think most of you are familiar with, right? Melting. What happens when something melts? Solid to a liquid. So, what has to happen when something goes from a solid to a liquid? Let's go more generally.
The particles spread out a little bit more and they
Move faster and spread out more. And Lauren, that means what about the attraction?
it's less.
Okay, so more energy, less attraction. And because of that, we need to gain energy. So, particles become less ordered. They vibrate and gain more energy. And then they break free of those fixed positions that they're in the solid. Less ordered, right? Particles vibrate and gain enough energy. And that means particles are no longer in those fixed positions that they're in when they are a solid. And all of that to happen, right? The particles need to gain energy, and that makes this an endothermic change. If you look up at the triangle, up at the very, very top left-hand corner, right? What other phase changes would also be endothermic phase changes? Liquid to gas, right? Because so far we know that gases have more energy than liquids, right? According to your triangle, what do we call liquid to gas? Vaporization, right? And then the third phase change that is endothermic is called what? Sublimation. When something goes directly from a solid to a gas. There aren't too many things that do that, but it does happen. Dry ice is one of the like most common thing here on Earth that does that. Say again? Gas to solid going the other way. We'll talk about that in a second. You can't get it from the You ever dry ice before? It's like it looks like ice, but it's not. It's carbon dioxide. It's not water.
Doesn't it burn you?
It can, right? It's actually taking energy out of you as opposed to putting energy into you. Okay?
It's like kryptonite.
Fire extinguishers have carbon dioxide in them, but it's still a gaseous state. But you could turn like you could use dry ice to help put out a fire if you let it turn into a gas, you know? So, because it goes straight from that liquid, or straight from the solid to a gas. Why didn't you get it? Yeah, you could. All right. So on the other hand, when something freezes, what happens?
Goes from a liquid to a solid.
Goes from a liquid to a solid. Underneath letter C. Underneath letter C. Go up to your triangle and look at the two things when something goes from a liquid to a gas and from a solid to a gas. Vaporization is liquid to gas. And then solid to gas is sublimation. Go ahead.
What's the letter C for like under B? Particles are no longer in
Fixed positions. That's what happens. In a solid, all those particles are in one spot, right? But when they go from a solid to a liquid, they're less. Okay? So, when something goes from a liquid to a solid, particles become more ordered. Energy decreases. And when energy decreases, what else happens? Attraction increases. Didn't hear you, sorry. So energy decreases, attraction increases. And that causes these things to start holding on to each other more and become nice and organized, like a solid. But in order for that to happen, those particles need to lose energy. And that's why freezing is an exothermic reaction, or an exothermic change. And that's where it can get kind of confusing, because a lot of times we think of exothermic like a fire. It's giving off energy. And fire is hot. That's true. But anytime something goes from a liquid to a solid, it has to give off that energy. And it has to release energy to the surroundings, and that's exothermic. Okay? So, just to finish up that back page, when something goes from a gas to a liquid, we call that condensation. And then when something goes from a gas to a solid, we call that deposition. So an example of deposition. When something, like in the wintertime, if we have a car parked outside, come back in the morning, windshield's covered with ice, right? It didn't turn into water droplets and then freeze. The water vapor in the air just went straight to a solid. Now, that only happens when it's really, really cold outside, because those particles in the gas have to lose a lot of energy to go straight to a solid, but it does happen. Okay?
But she doesn't make
Hey, there is some homework on the calendar. Check it out. Lab tomorrow.
my lawn